So thank you very much. It's really a pleasure to be here tonight. So first of all, I would like to thank the BCS and the BCS staff for organizing this. It's really great. And I would like to thank the organizing committee and the people that actually nominated me for this award. And of course, as any work that actually leads to a prize is never done by one single person, but it's always a team that actually does the work, right? So I would like to thank the core team that actually did the work. So Cristiano Calcagno, Peter Hearn, and Honsak Yang, we did this work as a kind of team, and then all of us bringing a lot of different kinds of strengths, a lot of ideas, but all of us really a lot of work. Also, part of the work that I'm going to present today is joint work together with other people, with Josh Bardine, Byron Cook, and Thomas Wyss. And also, during the years, I've been working with many people, and all of them helped me in several ways in doing different kinds of things and to grow and to learn a lot of stuff. So I would like to thank all of them. Thank you. So, right. Okay, so several years ago, in 1997, I was doing my master thesis in Pisa, in Amsterdam, at the same time. And I decided that I'm going to work on semantics and logic. And the reason why I thought I'm going to do that, because I thought actually this topic is really beautiful. It's kind of pure, and it has some kind of really nice concept. And part of the beauty that I found in this topic was the fact that I thought it was useless. And in fact, when then I saw this quote by Andy Warhol saying, an artist is somebody who produces things that people don't need to have, but for some reason he thinks that it would be a good idea to give them, I thought, oh, this is actually great. It fits precisely what I'm thinking. So I took this quote and I put it on in the first page of my thesis. Then I went to Twente in the Netherlands, and I was studying for my PhD. And for the first time, I saw actually application of logic into solving problems, so particularly like verification. But still, I was still working in a kind of very theoretical side of this topic. And then I moved to London, and in London I met many people, and I learned many things, and I kind of changed my mind. In the sense that I kind of realized that, well, maybe logic and semantics is not that just beautiful just because it's useless, but also because it's like intrinsically beautiful. And so I thought that, well, actually, if we can do good things with it and useful things, then I think we should do that. And I met people like Richard Bonat that would say, well, I want to prove programs that actually people write. And I thought, oh, that's great. I want to do the same, but I don't want to do only that. I want to also I want to prove programs that people write, but also programs that people use. And the reason I want to do that is because I think so there is like a lot of software out there that is used every day by millions of people, and it comes like with critical mistakes. And I think this is not good because this commercial actually says that. So this is the commercial of the iPhone. It says like there is an app for that, meaning that whatever you want to do nowadays, there is an application that you just go and download it and you can do it. In fact, I think they reached the 1 million number of applications. So basically what is happening nowadays is like everybody is like doing more and more things with software, with the phone, with computers, with tablets. So what we do, every day we do more critical things with our software, but it's just common software, right? It's not like safety critical software or that has been created in a special way. But still, because we do more and more things that are critical for us, like, I don't know, we connect to the bank account, we move money, we pay, and so on, it's becoming critical for all of us. Yes, so let me give you an example. So this graph shows the activation rate of Android's mobile phones that now they have like the the biggest share of the market. So you can see like there's a lot of activation every day. In particular, there are like 700,000 activation of Android mobile phone every day. So the mail online saying there are more Android phone activated every day than baby born. So we are getting to around like 250 million units of these phones. So really widely used kind of software. But also, for example, now NASA want to use them to build satellites. So they say like, well, we don't need to actually take a computer and put it in the satellite. We can just put an Android phone on the satellite. It's enough because it's fast. It's fast as a computer. It's dual core. It is cheap. It has a camera, GPS, and so on. So we are going to build a satellite like that. So basically, there's a huge use of this kind of devices. And yet, so they come with critical errors. For example, like here, there's a piece of code that comes from the Android operating system. And here you can see one of the critical mistakes that basically there are there. For example, this is a memory leak, which means that it's a kind of so the software is going to start to lose memory at some point, and will lose more and more memory, and this will make it the system goes slower and slower until it's going to crash completely. So another good example, I think, of software that we use, that many people use every day, like millions of people use every day, is Apache. Apache is the most used web server in the world. So we have like 65% of the internet run on Apache. So basically, every time we connect to the internet and we visit a website, most likely we are using Apache. So all of us is using it. Millions of people is using it every day. And yet, it comes with critical errors as well. So here, this piece of code of Apache, and this shows a problem called null pointer dereference, which will make, if exercised by the system, is going to make the system crash. OK, so another problem, computer security, that is becoming really, really hot at the moment. Since we are doing all these kind of critical things with all these applications, and all these applications, they always send you things, your data online, and it's becoming a big issue. And we see it every day on the news. So here Bloomberg says, OK, there is some cyber attack on banks. The Telegraph, Britain is targeted up to 1,000 cyber attack every hour. New York Times, IMF report cyber attack. So it's like if you look at the news and you look at these kind of things, you can see it like every day. I mean, I've been checking it, and it's kind of amazing. It's becoming such a big problem that even governments are kind of taking notice of this kind of problem. In fact, that's what Leon Panetta, the US Defense Secretary, is saying. It's like the next Pearl Harbor can actually be a cyber attack to our software infrastructure, for example, the grid or the financial system. But what is, I think, interesting for us to notice is like around 50% of the problem that generates security issues are coming from coding mistakes. So this kind of mistakes that I showed you before in Apache, or for example on Android, those are kind of mistakes that, for example, may lead to security issues. Okay, so of course there are many others. But many of these issues come from coding mistakes. So it is clear to say, it's kind of fair to say that actually whatever we could do to improve the security and the safety of our code is a good thing to do. So what I'm working on, and what me and my colleagues work on, is a technique called automatic software verification. So in a very general term, what it is, you have like a system called the verification system that on one side it takes some kind of some program, some code, like the one that I've shown you before. And then on the other side, they take a property, and they try to make some computation and try to see if the code satisfies the property. So, and the verification system can say yes, if this is the case, if we manage to prove that. Or it may say no and give you a reason why this is not the case. Or it might say, I don't know, because this is one of the verification is one of the example of undecidable problem. So there might be a situation in which we cannot, it cannot be decidable to say if it's yes or no. So there might be cases when you say, I don't know. So now what we can prove like things like functional correctness. So we could try to prove that the system does what it was designed to do. But we can also prove things like the system is not going to crash, or we can prove that the system is not going to leak information or is not going to leak memory. And this kind of properties, like the system is not going to crash or leak information, are kind of general properties, fundamental properties that every system needs to have, right? So they are like the basis before, for example, we want to prove that the system has the correct functional correctness. Okay. Right. So so in the last 10 years, we have seen like great advances in software verification. So there have been like incredible tools that have been created. Like for example, the SLAM tool developed at Microsoft for verifying a certain number of properties for device drivers. But also the Astray tool, the Astray analyzer that was used for verifying avionic code at Airbus. So this kind of tool have done like really great advances. Before it was not possible actually to run on real industrial code and so on. But what they were missing was the treatment of dynamic allocated data structures and pointer manipulation. So what is that? Well, so this kind of the tools before, they had some kind of view of the memory that was kind of shallow. So they were seeing a part of the memory, but they would kind of skip another part of the memory, which is called the heap, that is kind of complicated. So let's open this heap and see how it looks like. So there, what you could do, you can actually allocate some block of memory. So you can have things like that can appear. And then this block of memory, they can point to themselves, so they can have some reference to one to another one. And then during the computation, this can grow and become more and more complicated. Okay? So in fact, somebody called this spaghetti pointers, because the picture become really, really complex, and it's very difficult to actually make sense of what is going on there. So this was before for automatic tools was very difficult to understand and was very difficult to actually deal with. In fact, it was so difficult that Tony Hoare said that the introduction of pointers in high-level languages has been a step backward from which we might never recover. But however, there is a lot of code out there that actually make a heavy use of pointer manipulations and dynamic allocated data structures. So, for example, the software that I showed you before, like for example Apache or for example Android, or this is a picture of a device driver. They all make heavy use of this kind of techniques. So what we want to do was kind of work on this kind of problem. So trying to reason about this kind of spaghetti code in an automatic way. And what we want to prove for this kind of program was like they are not going to crash, they are not going to leak memory. In particular, that we actually are able to manipulate this kind of things in the correct way. Right. So, and in order to do that, an analysis or a verification system that does this automatically, that try to reason about this kind of spaghetti code, is called a shape analysis, because it has to compute the kind of shapes that this graph will have. And this can be very, very complicated. In fact, it's complicated to actually compute this kind of shape, but also when you make a verification, you have to compute all of them. And there are an enormous amount of this kind of shapes. So in fact, up to 2006, there were the old techniques that were known. They were able to solve the problem only up to very small program, like 100 lines of code. So in principle, there was some kind of chasm between like the theory and the real world. In the real world, we had like millions of lines of code code out there that used like pointers and dynamic allocated data structures. On the other hand, we had kind of theories that are able to only work with very small, tiny program. And I remember when around 5 years ago when I went to interview for my Royal Academy of Engineering Research Fellowship, I said that what I want to do in this fellowship is like to cross this chasm between the theory and the real world in terms of reasoning about dynamically allocated data structures and pointer manipulation. So that's where this work comes from. Right. OK, let's go back to the picture I showed you before. So we want to build this kind of verification system. And for this, the kind of properties we want to prove is called pointer safety. So basically that the system is not going to crash, it's not going to leak memory, no information, and so on. So the first thing we need to do is like we have to formalize what pointer safety actually means. So, and we are going to do that using mathematical logic, in particular one special logic called separation logic, which actually was a logic invented around 10 years ago that actually has brought very good advances in terms of reasoning about this kind of spaghetti pointers. So the reason is that they have found a way to simplify the reasoning so it becomes much easier to actually make proofs about this kind of problems. And the way it is done is like by the introduction of a new kind of operator that actually separate the meaning of assertions. An assertion P and an assertion Q that actually express some configuration of the memory, then you will say like you have P and separate Q. Namely that these two formulas denote two separate pieces of memory. And this make incredibly enough, at least for me, I mean, I was really surprised that this make the reasoning really, really easy. So for example, here there is like a proof of a program of 3 lines of code, the one highlighted in yellow, done before the advent of separation logic. As this is like, it's pretty complicated, there is a lot of math and only 3 lines of code. But then with separation logic, it becomes much, much easier. So the reasoning becomes simple, neat, it's really great. So we thought, okay, this is like the great, a really good device, a really good theoretical device that we can use as a basis for us to try to automate this kind of reasoning. So we started from there. Okay, so then let's see what is the verification system. So the verification system is like it is a kind of system that has some kind of internal representation that is a symbolic representation of the configurations that the computer memory has. So basically, some kind of symbolic representation of the spaghetti pointers. So for us, this kind of representation is done with using formulas in separation logic. Then what the system does, symbolically execute all the possible states and all the possible configurations that the software will have when it is going to run. And this is done by kind of not running the program, but kind of computing all the possible configuration that the system can actually be at runtime. And this is done by defining some kind of mathematical rules that says like how a configuration is changed after the effect of the execution of a code. So for example, like because in our case we have like formulas to express the configurations, then we will have like rules that say like how a formula change after the execution of a piece of code. Right. So, but let me be a little bit more concrete. So for this, let me introduce you a friend of mine, Jeff Leach. He's an actor, he's a comedian, he's also a TV presenter, and so on. So Jeff have many shows every week. So what he does, he always have this kind of guest lists, and so that he put his friends there, and then his friends can go for free to the show. Now, on that side, we have like a little code that should help Jeff to build his own guest lists. Okay. Now, suppose we were to analyze this kind of code with a symbolic execution, right? So, as I said before, what the symbolic execution will do, will try to actually compute all the possible configuration that this program can have at runtime. So, it has to compute all the possible guest lists that Jeff Leach can actually have. And he can have like very long guest list. I mean, it's the only person that I know that discovered that if you have more than 5,000 friends on Facebook, they just block your account. So, so basically, so you have to compute all these possible lists, and there are so many that what we have, like, if the symbolic execution would try to compute all of them, it will never terminate, because there is an abundant number of them. So by itself, the symbolic execution is not an effective method to do actually analysis of programs that manipulate dynamically allocated structures and pointers. So what we need to do, we need to add something more. And in particular, we have to use abstraction. So abstraction is a kind of very general thing in computer science, right? So it's used for all sorts of things, but we are going to use it in a very, very specific way. So we are going to use it in order to have shape abstraction. And the reason is because what we want to do, because we want to reason about like the crash of the system, to prove that the system is not going to crash. And in order to do that, we have to reason about this kind of shapes, this kind of spaghetti shapes. So we only need to care about shapes, and we can actually abstract away all the other information. So now here I've shown. So I have one formula here, the green one. That actually is a formula in separation logic that says like you have a guest list of three elements. Okay. And it's basically a representation of that picture there. Now, what we want is like, because we only care about the shape, we can just say like, actually, if I have a node n that points to a node n double prime, I don't need to distinguish between the two of them. I can just say that I have a list that starts from here and up to there. Okay? Then, if I have a list followed by another node, again, because I just care about the shape, I can actually forget about the distinction between these two, and I can say, well, I only have a list that starts in the beginning and then a nil, where nil is like the constant that denotes the end of every list. So what we have done here is like we have abstracted away from the sides of the list. So in a sense, here we have the information that the list is only 3 elements, whereas here we don't know this anymore. So this is a kind of more abstract representation of the list. And this kind of list now represents all the possible lists that start in the beginning at n and finish at nil, and they can be of any size. So we have like a more compact representation for many of these possible lists. And what we are doing there, by doing this, we are just defining an abstraction function that takes a configuration and is going to give you back an abstract configuration that represents more possible different states in a more abstract way. And this is done by defining some kind of abstraction rules that are like mathematical rules like this. So we don't need to understand that, but the only thing we have to see is like what these kind of rules do. They just take a formula that is a kind of representation of a configuration and give you back another formula that is a more abstract configuration. Okay? So we only care about that. And if you really want to know what this precise rule is doing, you're just saying like, well, if I have a node here followed by a list and I don't care about this middle point, I can just forget about it and say I have a list that starts from here and then end at the end. Okay? Now, when you do that, basically what you get, so you can actually prove a lot of nice things. And the thing you can prove are actually this, that we actually care are the last 3 things. So first of all, that this abstract representation is an over-approximation of all the possible states that the software will have at runtime, which means that when we use the abstract representation, we are not going to lose any possibility of the kind of situation where the software will be at runtime. Also, the other important thing is like this kind of representation is finite. So if we combine this with the symbolic execution, the fact that we compute the symbolic execution over a finite representation, the symbolic execution will always terminate. So this will give us a kind of effective way to actually do automatic verification of pointer programs, so programs that manipulate pointers and dynamic allocated structures. And in fact, having that, it gave us like really an effective way to do that. And in fact, we could implement this and create our first tool, which was called Space Invader, that actually represented the first automatic verification system that actually was able to prove programs that manipulate pointers and dynamic allocated data structures. So this was actually great because we could basically take all the possible programs that there are in the literature, and we could automatically verify all of them. And it was working very well, and we could even take some kind of algorithm from textbook and so on. So it was working very well. And at that point, we said, like, well, maybe we can just go and try to look at some more real industrial kind of software. So we went to kind of look at this, and they told us, well, go and look at device drivers, because device drivers are like programs that are manipulating lists, so your technique should be good at it. So we went to look at that, and what we found like very complicated kind of structures. So we start to look at the code of device drivers. So you could see, like, I don't know, in 10,000 line device drivers, like 10% of that were only like struct definitions, where all these definitions are like a lot of reference between them. So actually it could be a real spaghetti pointers kind of picture that they were manipulating. So it was not clear what they were doing. So this picture here shows some part of code of a device drivers, and that actually turned out that the kind of data structures that device drivers that will manipulate would be something like that. So it would be some kind of a certain number of circular double linked lists with nested a certain number of linked lists. So here I just draw a part of it because it couldn't fit into the screen. But as you see, I mean, it's a much more complicated kind of structure with respect to the thing that we were seeing before. So, and in particular, in this case, the techniques that we had before, it would not work. So we went back and then we started to think about this for a while. And then what we came up with was a concept, this concept of adaptive analysis, which means that what we want to do is like to create an abstraction system that actually understands on the fly while it's trying to analyzing some code, which kind of data structures will be there and the way that this can be abstracted. In particular, the system will try to find certain kind of patterns, certain areas that are like similar, so that it's going to combine them together, kind of make it some kind of building block, so that it can be used afterwards to be abstracted in a bigger block, and so on and so on. So we're going to do something like these dolls that you put one inside the other one, okay? Let me show you how this works. So if we were to abstract this kind of system, what the verification system will do was first try to abstract the simple list as we have seen before. So something like that. Okay? Then it can do this also on the bottom. That's okay. Then it will be able to maybe abstract a circular double linked list. But then at this point, nothing will work of the fixed kind of abstraction we have. So it will start to actually use this adaptive feature where it will try to understand how we can abstract this kind of technique, this kind of configurations. So it will look around, and it will actually notice that there are certain areas that look similar. So for example, this kind of area here, they are all similar. So it's going to decide that it's going to make a building block. It's going to wrap this and going to create a yellow box. Okay? And then you will notice also that actually here there is some repetition as well. So you can actually try to simplify the picture by kind of abstracting this kind of shape and making just some kind of predicate that describe that kind of shape. So you will get the situation. And as you see now, the configuration become easier and easier, so the picture becomes simpler. So at this point, you can actually say, OK, I have some kind of double linked list of this yellow block. So I'm going to abstract and make a list of yellow box. And here, I will make a list of green box. OK? So at this point, when the analyzer will get to this point, then it will have a very abstract kind of configurations, and then this will be enough for actually terminate for the analysis to converge. Okay. Now this system actually worked also pretty well because it allows us to verify all sorts of routines of device drivers in Windows and Linux. And the good thing about it was that we don't have to actually commit at the design of the logic which kind of predicate we need. But those are actually discovered on the fly. So if you have different kind of configuration with different kind of shapes that different kind of software will have, the analyzer will adapt on the fly or what kind of logic predicate it needs in order to abstract this kind of software. So what we get there was like for the first time we were able to actually analyze automatically some industrial code that does pointer manipulation and dynamic allocated data structures. And this was kind of really, really cool because we could analyze all sorts of routines of device drivers for Windows and Linux. And then also after some crazy optimization that Honsock did, we actually managed to even get to verify complete device drivers up to 10,000 lines of code, which was a kind of a big landmark at that time. So this was great. But then I said, like, actually, I want to prove, like, as I said in the beginning, I want to prove programs that people use. And those programs have millions of lines of code. And this kind of technique essentially kind of show us that we reached the limit. We couldn't just go beyond this kind of wall of 10,000 lines of code. So it was clear that we need actually something different. But let me try to explain what was going wrong at the time. So the abstraction techniques actually was pretty good because it was kind of flexible enough to adapt to many kind of different data structures. But the problem was like that we were using some kind of standard technique called whole program analysis that tried to analyze a program that is composed by many routines. So suppose that these are like procedures of the analysis. Then what it would just go and start to actually compute a big analysis that goes all through the program and visit all the procedures until it goes to all of them and say, yes, the program is all right. And this works well for small programs. Now, when you have bigger programs, it's a bit more complicated. It doesn't work so out of the box. Okay. So because like sometimes you don't have the real program, so what you need to do is like you will need to write certain kind of routines that will create the right data structures that you have to give to the procedures that you want to analyze. So then after you write this procedure, then you will start to do a big analysis that will go through all the procedures. And then at a certain point, something goes wrong. Okay? And things go wrong for many reasons. Okay? So one possible reason would be like this kind of proof that is kind of creating is too big, is not going to fit in memory. And basically, it's not going to fit in any possible memory that we can think about it. Or maybe that the program will have some kind of construct or some kind of is trying to do something that actually doesn't fit with the mathematical model that we have behind. But the problem is that as soon as one thing goes wrong, what we have done so far, all the things we have constructed just falls apart, and we lose everything. Okay? So in this way, it's like it's really difficult to actually make this technique actually scale. But as I said before, what we want kind of democratize program verification, right? So we want to have like a push-button technology so that developers are able to use it, but also we want to that this technology actually scale to the size of the programs that actually people write and use. Okay, so the previous situation, which was this one, where you get some code and then you do some manual work to write some routines yourself, and then you get to the point where you actually can start the analysis, and then maybe you are lucky it's going to scale up to a point like maybe 10,000 line of code. We were lucky to get to that point. It's not enough actually, because what we need to make it really democratic would be this, right? A picture more like that. We need to get the code, have the possibility to push the button immediately, and then this has to scale up to millions of lines of code. That's what we want to get. So how do we do that, right? Well, what we want to do is to use the principle of compositionality, the Frege principle in semantics that says the meaning of composite expression is determined by the meaning of constituent parts. So we want to translate this to program analysis and verification, and we want that the analysis result is computed out of the result of the analysis of the part of the program. Okay? So what we want is more pictures like this. So we have this big program with many routines. So this is going to start to create little proofs here and there, and then sometimes something goes wrong, but this will not stop us to continue and try to prove routines that are not related to that. And then what you do, you combine proofs that you have done before to make bigger and bigger proofs and to try to cover more and more part of the program. So that's the idea. So I think it's quite simple, but the question is how do we do this, right? Technically. And it was not that straightforward. Okay. So now I'm going to enter more in the kind of technical part of the talk. Okay, so stay with me. Okay. So what we want to do, we want to do some kind of compositional symbolic execution. So when we have when you prove a specification in separation logic, like this one, basically you have proven that that kind of routine, dispose, is not going to crash. Okay, and in particular, this part here, which is called the precondition, is telling you which kind of resources you need to run the procedures in a safe way. Okay? Now, so I said that we want to do things in a compositional way, so we want to reuse the proof that we have done when we are going to, in piece of code that actually use dispose. So if we want to prove something that actually call dispose, what we want to do is not to analyze this again, but to reuse this proof that we have done before. So if we have some calling context with who you want to try to analyze this, what we need to do is to have an implication between the calling configuration and the precondition, so the kind of resources that the procedures need to run safely. Okay? And now, to do this, it's not kind of trivial, okay? When you want to do it in a compositional way. So let me try to explain why with a kind of real-world example. Okay, suppose that you are Italian, like me, and you want to drive your Fiat 500 in the street of some small Italian city in the southern Italy, okay? So you take your car, and then to drive your car, you need some resources, right? So you go to the gas station, and the gas station, you will have a range of gas that you can actually choose. But now, you won't need the diesel, and also you don't need the premium because the car is old, so it's okay to take the regular one. Okay. So, but also in order to drive this car safely, you will also need some kind of extra resources. For example, you will need oil and water. Okay. Now, what you have is you have in front of you, you will have some certain kind of resources that are there, but you don't need it. But also there are some other resources that you needed, but they are not there. And they might be somewhere else in the shop of the gas station, but they are just not in front of you. So now we are going to be in the same situation. Every time we want to construct the proof compositionally, we will have a certain number of resources, some of which we need it, some we don't need it, and some resources we need it, but they are not there. And we have to find them. Okay? So we are going to play this kind of game. Now, for the resources that are there and we don't need it, that is called the frame, by the way. I wrote it in the previous slides, but I didn't say it. Separation logic has a kind of good way to deal with that. Okay? So it would allow you to take a proof and actually reuse it in the context where you have some strictly more resources, so where you have some frame. Okay? This part R. Okay? Now, when you want to actually use this kind of rule in a kind of automatic system, what you need to do is like to compute what is the frame. In order to compute the frame, you need to have a theorem prover that is able to solve this problem here, frame inference problem, which means that when you're giving a configuration A and B, you need to compute some extra stuff, some extra resources that you put it together with the B, so you have some implication there. So if I make an example with the proof, so suppose you're proving this kind of things together, and you want to reuse the proof of dispose, which is this one, and you have this in your hand. What you want to do is like compare what you have and what you need, and then you say like take your theorem prover, and your theorem prover should tell you what you don't need. So it has to calculate the frame. Okay, so you call your theorem prover, and then the theorem prover should be able to compute what is the frame. So you need to construct a theorem prover that is actually able to answer this question. And when you have that, well, you can identify what is the frame here, and you can use this rule in separation logic to make the proof. Now, this on one side. Then on the other side, there was like the kind of resources that we don't have, right? So for doing that, it turns out that what we need is the concept of abduction. Abduction is a concept in logic that was introduced by Charles Peirce in the beginning of the 1900s when he was writing about the scientific process. So basically, abduction is the process of coming up with a new hypothesis that allowed you to explain a certain kind of surprising event. So here's an example. Eratosthenes was a Greek mathematician, a Greek scientist that was living in Egypt, in Alexandria. He was working at the library. Okay? And so he learned that in the city of Syene, in the south of Egypt, the day of the summer solstice at noon, the sun is at the zenith. Okay? So it's perpendicular. But then he knew that at the same time, in the same moment, in Alexandria, this was not true. So in order to explain this kind of surprising event, he hypothesized that actually the Earth must be round. And when he makes this hypothesis, what he's doing is doing an abduction. He's created this new hypothesis that is able to then explain this kind of surprising fact that actually the sun is in two different positions in two different cities. So what we need to do something similar in our case. So what we need to do, we need to try to compute what are the hypotheses that we miss in order to actually make something true. And in fact, we need to solve this problem, which is the abducting inference problem that says, like, if I have a configuration A and B, I need to compute some extra resources that I need to use on my hypothesis in order to make the fact be true. So if we bring this in terms of constructing a proof in a compositional way, this will mean that if I'm proving this piece of code where I'm using the dispose to list procedure, and we have a proof for dispose to list that says that I need this, then what I do, I take what I need, and I compare with what I have, and then I'm going to ask an abduction question, and my theorem prover should be able to tell me what I'm missing in order to have this implication here. Okay? So what you need to do, you need to construct an abductive prover that is able to answer this question. So, and when you have that, well, it might compute something and says, like, well, you actually missed this kind of part, and this part should be added to your calling state in order to call this in a proper way. Now, in reality, what you actually need, as you are always in the situation in general where you never have like something strictly more or something strictly less, but you have both of them, right? Remember the example of the Fiat 500, okay? So what we actually need to do is like to compute the frame inference and the abduction problem at the same time. And this is like brought to this new notion called by abduction, that is precisely this. If you have a configuration, another configuration, what you need to do is to compute an anti-frame and a frame such that you add some extra resources that you miss, and you exclude certain resources that you need, and then this implication would hold, and then you can actually construct proofs in a compositional way. So let me show you how this works. So I'm not going to go into detail how it works, but the only thing we have to notice here is like if we are trying to construct a proof for this function p, and this function p called the function foo at some point, and we have proven something for foo, we want to reuse this proof here. So at some point, we will get to the point where we have to call it. So in order to keep on constructing this proof in a compositional way, then we are going to call the biadaptive prover that is going to tell us what we miss in our calling context and what we have extra that we don't need. So it's going to give us some answer. And so it's going to give us the way to continue the proof by reusing the proof that we had. Okay? So it's going to give us this ability to go and construct the proof really in a compositional way until we get to the end. Right. So at this point, we construct a proof for P. And we did this by reusing this kind of part. Now, the great part of this is like actually, by doing this, is like it's really compositional. So what it does, it actually scale on large code, and also in an automatic way. Because basically what we do, we analyze parts of the code in isolation, so we don't need to actually construct part of procedure ourselves in order to start an analysis. But also because we construct little proofs and we combine them together, we don't have to construct this huge proof, so that we can start to build little things and grow so that it can fit in memory and it can actually scale in the right way. And as you see, like this graph shows you the scalability of our technology. So now you can actually run on real code that actually people use. For example, Apache, the one that I showed you before, OpenSSL, Linux, and Android, which is our biggest benchmark we have, which is over 5 million lines of code. And the cool thing is, once you start to run on big code, and then what you get things like that, a bunch of errors, like OpenSSL, null pointed reference, null pointed reference, null pointed reference, and so on. Like a bunch of stuff, like Apache, memory leaks, null pointed reference, null pointed reference, and so on. And so you can SQLite, memory leak, and so on. So you can actually fill up really a lot of screens with all this kind of mistakes you can actually find automatically in this kind of code. So, I think it's like I get almost at the end of my talk. So let me just say a few words at the end. So in retrospect, I thought it was like kind of, in this last year has been like an incredible journey that went like all the way from really nice theoretical result in logic up all the way down to actually trying to analyze very dirty code that developer write, but people use every day. So we started somewhere in East London at some point a few years ago with some results that we learned on separation logic. Then we went on by constructing the first kind of automatic abstraction and automatic tool that managed to prove the first kind of programs that manipulate pointers and dynamically allocated data structures. Then we went on with more sophisticated kind of abstraction, where we had analysis that managed to adapt to the different kind of configuration and complicated stuff that you can have on the software. And finally, we got to the point where we can actually run it on big code, because we managed to find a way to do this compositionally using this notion of abduction. So, of course, there's still a lot of work to do, so that's great. So I'm not going to be bored for the next few years, and the same like all the people that work in this area. There is a lot of stuff to do, a lot of space still to explore. So basically, I think that this journey is to be continued. Thank you very much.